Hello everyone. Welcome to this session on algorithmic problem solving. In this session, we would like to consider the problem of finding the shortest paths in a weighted directed graph, from a designated source vertex S to all other vertices in the graph. Specifically, we will be discussing Bellman Ford algorithm.
Set G, H set E, and weight function W, we wish to find the shortest path in this graph. And there are some variants of this problem. So just before we start the problems, let us look at how the graph is set up initially. So on each edge, there is a weight WUV, and WVV is 0 for every vertex B. And for vertices U and V which are not connected by an edge, WUV is set to infinity. So this is the initial set of values for the weights. So given this weighted directed graph and this weight function are defined as we have said just now, cost of a path is the sum of the weights of edges on the path. And given designated vertices S, which is the source, and G, which is the goal, we want to find the shortest cost path in the graph capital G from S to small g, which is the goal node. So this is the basic statement of the single source problem. And here we are assuming that we have a single destination node G. Of course, the more common variant that we come across is the single source multiple destination. So we have a weighted directed graph G as we have already defined, and the cost of the path is sum of weights on the edges of the path, but you are given a single source node and you want to find the shortest path from this designated source node S to all other vertices in the graph. So before we describe any such algorithm, let us first try to mention one very important issue regarding negative weightages. So if you look at this example, we have a part of a graph being shown with vertices A, B, C, D, and you can see directed edges going from A to B of weight 2, one going from B to C of weight -3, and a directed edge going from C to D of weight 4. So there is a negative weightage BC. Now one may ask that what is the significance of negative weightage in a graph? One common idea that we have is graphs with weighted edges necessarily represent road networks. And yes, you have on a road network, you have these edges which are road segments, and the weights represent the distances on those road segments. However, remember that the shortest path problems are not necessarily all road network problems. We have some shortest path problems representing some maybe some chemical reaction or something, and where the edge weight could be the heat produced during that reaction, which could be positive or negative. So there are various physical phenomenon being modeled as graphs and graph problems like shortest paths, and where negative weightages may arise in practice. So we need to handle negative weightages with care. And why this assumes significance is, let us look at this little example that I have on the slide here. So we have a graph with 5 vertices A, B, C, D, E, and as you can see that there is an edge which is of negative weight. All the other edges are of positive weight, and then this edge going from C to D, this is a negative weightage, -5. So now what is the significance of this? So let's try to figure out what is the shortest path from A to E. So from A to E, if I go via B, the path length is 2, right? So A is 1, AB is 1, and then B is 1. So 1 plus 1, 2 is the cost of the path ABE. Now, I may take a detour, right? So I may go from A to E, A to B, and then from B to C, and then C to D, and D to B, and then go to E here. So what is the cost of the path now? So that's my 1 going from A to B, 1 going from A to B, and then plus 2 going from B to C, and then a minus 5 going from C to D, and then a plus 2 going from D to B, and then a plus 1 going from B to E. So the cost is 1. If you add up the numbers, you'll see that the cost is 1. Right. So the previous cost A, B, E was 2, and then we can reduce that cost to 1 just by making a detour via C and D. Now, if you are clever enough, you see that you can actually go around this loop twice. If you go around this loop twice, in each round of the loop, you incur a cost of -1. And therefore, if you go around twice, you'll get a cost of -2. And then your cost of going from A to B, A to E will be 1 minus 2 plus 1, which is 0. So we can reduce the cost of going from A to E to 0 by going around that loop twice. Uh, Now, of course, one may ask what happens if we go around this loop 3 times. So each time, so if you go around this loop once, you'll see the cost incurred is 2 minus 5 plus 2, which is essentially 2 plus 2, 4 minus 5, which is -1. So the cost is actually -1 for going around this loop. So which means if I go around this loop 3 times, I can reduce my cost by 3 units, which is my cost of going from A to E via B, which was 2 units, can be reduced by 3 units. So my cost will become 2 minus 3, which is -1. So I can play this trick as many times as I want. I can keep going around that loop 10 times, 20 times, and my cost will keep going down. So the cost of the shortest path from A to E is something that cannot be taken because you can make it as low as possible as you want. Okay, so this is the reason why we sometimes shortest path edges, shortest in path problems and shortest path problems, negative weight edges assume significance, and we need to be careful because sometimes the shortest paths may not be determinable if you have negative weight loops like this. So we'll come across algorithms which do not work for negative weightages, and there are others which do work, and we'll distinguish between the two when the time comes. Okay, so this was what we were discussing just now. The shortest path from A to E actually does not exist because you can keep going around the loop BCD as many times as you want, and then you can make the cost of the path as low as you want. So before we get on to any algorithm for the shortest path problem, let us go through some very simple definitions to make our descriptions clearer. So we'll let delta V be the cost of the shortest path from S to V. So remember, we are trying to solve the shortest path problem on a directed graph with a designated node S, and we want to find the shortest path from S to all other nodes B. Not equal to S. This is the variant that we are trying to solve. Single source, multiple destinations. We have a weighted directed graph, and we want to find the cost of the path from a designated source node to all other nodes in the graph. So we'll denote as delta V the cost of the actual shortest path from S to V. Let dV be the cost of the shortest known path from S to V at any point of time during the algorithm. So dV is a value that will keep changing during the algorithm. Delta V is a constant. For a vertex V, delta V is the cost of the shortest path from S to V. Okay, and dV value is an estimate of the path. We'll keep refining that as the algorithm progresses. And our goal is that finally, when the algorithm ends, dV should be equal to delta V. That means we have determined the correct values of delta V for all vertices V in the graph. Starting from S to all other nodes B, we want to find the cost of the shortest path from S to V. So initialization, Initially, the DS values are all set to 0. DS value is set to 0. That's for the designated source node. And the DV value, all the DV values are set to infinity for all other nodes in the graph. And the DV values will be gradually revised or reduced as the shorter paths from S to V are found. So maybe just let me go to the whiteboard once. Okay. So if you look at the DV values over time, right? So this is my time t, and this is my DV value. So what is DV value? Remember, so what he said that you have the designated source node S, and V is any vertex in the graph. And here is my shortest path from S to V, which I have not yet determined. And I estimate the delta V is my cost of the path from S to V, which I estimate with a value dV. And to start with, dV values other than for V equal to S, any other dV value is set to infinity. And as we discover shorter paths from S to V, we keep refining the dV value. Okay, we have found another shorter path, so the dV value drops again, and so on. And then finally, the dV value drops to some number, and then does not change anymore. And that's when you have actually found the shortest path. Right? So this is the delta V value. Right? So dV value is initially set to infinity, and then it gradually drops down to settle down to the delta V value at the end of the algorithm. This is how the algorithms will be structured. We'll try to refine the estimate of the delta V with the dV and gradually take it to the exact value delta. This will be the structure of the algorithm. So we'll see how to do that. Let me get back to the slide once more. So we defined a relax operation UVW. Relax UVW. So if du plus WUV is less than dV, then dV is equal to du plus WUV. What does this mean? So here is I have a vertex U. I have another vertex V. Here is my vertex S from where I am trying to find the shortest path from S to all other nodes in the graph. So I have found some path from S to U is known at this point, and the cost of that path is du. The best known path, the shortest path from S to U found so far is of cost du. Likewise, I have a dV value which represents the cost of the shortest path from S to V found so far. And now suppose in course of the algorithm, I discover that du plus WUV, so there is an edge going from U to V, and du plus WUV, which is the weight of the edge UV, is less than dV. So what does that mean? It means that it's cheaper to go from S to V via U than by the best known path from S to V found so far. Okay, so I'll repeat what I said now. So du plus WUV less than dV means it is cheaper to go from S to V via U rather than go from S to V via the best known path found so far. Okay. So which means we have discovered a better path than the best known path found so far. So what is the conclusion and what should be the result of this discovery? Result of the discovery means that the dV value that you have computed can be refined further. And so we refine that. We said dV is equal to du plus w to represent the fact that uh, dV should be equal to the cost of the path from S to V found so far, the shortest path found so far, and which we have refined by discovery of a new path via U. So this operation is called the relax operation. It's with respect to an edge UV. So if that edge UV helps you get a better path from S to V, we update the cost dV. So this is the meaning of the relax operation. So this relax operation is something really interesting and very powerful. And there are a whole lot of shortest path algorithms which are just built around the relax operation. So we'll look at two such algorithms. One is the Bellman Ford and one is the Dijkstra shortest path. So here is a description of the Bellman Ford algorithm. So initially, all the d values are set to infinity for all vertices except the source node. And for the source node, the d value is set to 0. And we repeat the following for v minus 1 iteration. So this is size of v means the number of vertices. So number of vertices minus 1. So we'll discuss later why this many iterations, why not more, why not less. We'll come to that point later on. So what do we do in this v minus 1 iteration? In every iteration, we relax all the edges in the graph in no particular order. Okay, so iteration 1, we go to all the edges in the graph and apply the relax operation. Iteration 2, we do the same. And the claim is that if you do this v minus 1 times, you have all the shortest paths. Okay, so why we'll come to that in a moment. There is also another iteration of the Bellman Ford in the end. So if the relax operation is successful of any age in this iteration, we report an error and terminate. And we'll discuss why this error and what is the significance of that short. Otherwise, the shortest path from all nodes have been found. To all nodes have been found. Shortest path to all nodes means from S to all nodes. So from S to, we're trying to find the shortest path from S designated node S to all nodes B, and at the end of the algorithm, the claim is all these paths have been found. If you look at the structure of the algorithm, it's remarkably simple. So all that we are doing is we have this function called relax UVW, which is applied on an edge, and what we are saying is go ahead and apply this relax operation on all the edges in the graph. In what order does not matter, in any particular order. Go ahead and apply the relax operations on all the edges of the graph and repeat this process v minus 1, and you should be done. Okay, so now let us try to understand why this works. Okay, so it is possible to do a very rigorous formal proof using induction. I'll skip that part, but I'll give an informal proof for justification as to why this works. Let me get back to the whiteboard. Okay, so in the Bellman Ford algorithm, we have a designated node S, and we have all other vertices in the graph. And when we start the algorithm, so there is a d value. We discussed this. So there is a d value which represents an estimation of the cost of the shortest path for west to node D, and we have a dv value defined for all the vertices. And the ds value is initially set to 0, and all other values are set to. Okay. So when we do a relax operation on all the edges, so remember what is Bellman Ford? It says in every iteration, do the following, go ahead and relax all the edges. And what is the relax operation? So we'll just quickly write it down for a reference once more. So you have a vertex U, we have a vertex V, and you have a edge between U and V. And this cost of this edge is W U V. And what the relax operation says is the following, that if du plus W U comma V is less than d of V, then set du set dv. Sorry, if du plus wv is less than v, yes, set dv to be equal to du plus w. Okay. So if you apply this on this graph, so this is not a graph. I have not shown the edges. There are arbitrary number of edges across various vertices. So the initial scenario, something like this, ds is 0, all the other t values are infinity. So if I apply this, so this is my relax operation. If I apply the relax on an edge which is going from a vertex with a d value infinity to another vertex with a d value infinity, what happens? Nothing. Right? So this if condition is not satisfied, and therefore nothing happens. So both the d values, so if I apply the relax operation on an edge which has a d value of infinity at either end, nothing happens. No d values are kept. If, however, if I apply the operation, relax operation on an edge u through v with a d value of 0 at u and infinity at v, then of course what happens is the d value at v changes from infinity to the value wu. So say for example, if I look at any graph and then wv is 3 and du is 0 and dv is infinity, and then dv will be revised to 0 plus 3, which is 3. So dv will become 3 after this iteration. So therefore, if I apply the relax operation on all the edges of the graph in one particular iteration, in the first iteration basically, what happens? So the only d values which will be affected will be the ones on vertices which are like one edge away from S, meaning the vertices which are directly connected to S, only those d values are affected. Okay, so those d values will be updated to the corresponding edge cost. Right? So if this edge cost is 1, this is I'm just taking arbitrary numbers, this is 3 and this is 2. So then these d values which were infinity, infinity, infinity initially will become 1, 3 and 2 after the relaxation. So what happens? In one iteration, after the first iteration, the shortest paths to the nodes which are connected to the source node via one edge, via a direct edge, those shortest paths have been found. And now these d values have changed from infinity to, so this has become 1 and this has become a 3 and this has become a 2 and so on. So what happens in the next iteration? In the next iteration, what is the next iteration of Bellman port? It says go ahead and relax all the edges of the graph again in no particular order. So we go ahead and relax all the edges of the graph, and again if we have a scenario like this, so if you have a scenario like this, we have a edge connecting a vertex with a d value infinity to another vertex with a d value infinity. Nothing happens. None of these d values are changed. So where the d values will change will be where I have a d value. I have an edge between two vertices where the initial vertex has some non-infinite value. It has some finite value. Okay, so 1, 3, and 2, for example. So now the edges which are so vertices which are connected by a direct edge to these three vertices 1, 3, 2, they will be those d values will change in the second row. So what do we conclude? That After two iterations, vertices which are two hops away from S, their d values will be settling down to the delta values. They will be the shortest path. The d values will represent the shortest paths from S to those vertices. So in general, so let me go back to the slides. So in general, the v minus 1 iterations are enough to find the shortest path from S to all the nodes. So in general, we can say that after k iterations, we will be knowing the shortest paths from S to all nodes which are k hops away from S. So understand that for any vertex in the graph, it is at most v minus 1 hops away from S. And why is that? So this is because if I have a graph here, this is my node S, and this is some arbitrary node V. And if I do not allow any repeats on the path, and my total vertex set is of size capital V. Okay, so this is the total vertex set in the graph. So I have only this many vertices, and therefore the maximum length of this path in terms of the number of edges on the path can be v minus 1. Right? I can only have v minus 1 edges on this path at most, and therefore in v minus 1 iterations we can show that the algorithm is able to compute the shortest path. So what happens if we do one more iteration after the v minus 1? After the v minus 1 iterations, we do one more iteration and we find that again some d values go down. The v values decrease some. So which means we are able to improve the d values even after v minus 1 iterations. And this can only happen if you have negative weight cycles, like that example that we saw in the class earlier on. Right? So something like this. So use a negative weight cycle and then you can go around it as many times as you want, and then you'll be able to reduce the cost of the path. So one can prove all these things rigorously, which we'll talk about in the next class. So for now, this informal argument should suffice that the cost of the path, shortest path from designated node S to all the other vertices in the graph can be determined in v minus 1 iteration. And should the vth iteration also produce some lower d values, newer d values which are lower than the previously computed d values, it basically means that there are negative weight. There is a negative weight cycle in the graph, and therefore you really cannot compute the shortest path costs with absolute correctness. So the algorithm simply reports an error and terminates. Otherwise, if the vth iteration, this extra iteration that you do in the end, right? So this after your v minus 1 iterations, you should be done. So you are doing one more round to do this error check. So if this round is successful, meaning that there are no changes in d values in this round, you know that you have successfully computed all the d values, the shortest path values. So the shortest path values to all nodes will form. Of course, here we are not finding the shortest paths, we are finding only the cost of the shortest path. The shortest paths specifically can also be determined by careful tracking of certain changes in the graph. As you, whenever you change the d values via some path, you have to remember that, and you can reconstruct the shortest path in the end. So I'll end the lesson here today. And in the next class, we will look at the Dijkstra's shortest path algorithm, which incidentally also is built upon the relax operation, except that it does the relax operation in a slightly different order. So one of the drawbacks of Bellman Ford is that it's very simplistic. So you are basically relaxing all the edges in the graph in every iteration in no particular order, but that leads to a lot of redundant relax operation. See, when you are actually trying to do a relax operation on an edge, which is connecting a vertex u with d value infinity to another vertex d with a d value infinity, it's a useless relax. Does not lead to any change of d values. Nevertheless, it costs you some computation time. And therefore, one of the drawbacks of Bellman Ford is that it does a lot of these useless relax operations, which Dijkstra tries to eliminate through some clever computations by keeping the d values in a heap and so on. So we'll see that variant later on. Thank you.
Thank you. This course is brought to you by Elahay Technologies.